Good morning. My name is Thomas, and together with me there is also the training expert Hanka. I am a sales director for sensors in Photoneo, and together with Hanka we will today introduce the 3D scanning devices of Photoneo. And during the first part that I will be holding right now, we will do a brief introduction of Photoneo, and then Hanka will go more in a depth in regards to the technology of our devices, on how to use them. We will also mention the software packages, and as I suggested at the very beginning, there will be a Q&A at the very end of the session. I hope that all of you guys know who Photoneo is, but just to make sure, Photoneo is a leading provider of the 3D scanning devices together with the software packages. We are coming from the Central Europe, from Slovakia. We are having our headquarters in Bratislava, and we also have offices in US and in China. We work with more than 45 distributors globally. So we are a true global provider of the 3D scanning technology. We have about 200 employees, and we have provided our partners with more than 3,000 solutions worldwide. We are possessing several global patents, and in our history of about 8 years, we managed to gather very important international awards that you can see at the bottom of the screen. What is Photoneo about? We like to say that we are providing eyes and brains to robots so they can see and understand what is around them. So they are capable of doing actions like random piece picking, depalletizing, packaging, sorting, or bin picking. All right, let's go to the next slide. I like this slide very much because it defines like where everywhere can our devices be used. We like to say that the vision guided robotics, or VGR, is something that our devices were made for. So definitely applications like bin picking, palletizing, picking and placing objects, doing the trajectory correction, assembly, packaging, but also the area of inspection and in reverse engineering, recognition of objects is something that our integrators or our partners can do together with our devices. I will also provide more concrete use cases just to demonstrate the use case. Okay, we'll use that. All right, let's go to the next slide. As you can see, we are definitely coming from the world of automotive. That proves our stability and robustness of our devices. These companies trust us. And lately, we also have been entering these verticals of logistics, but also the area of food processing and inspection in general. To explain like what devices of Photoneo, what technologies we use, is definitely it is structured light and parallel structured light. For those who are aware of the 3D sensing, there are multiple approaches and technologies that one can use. What is Photoneo uses is definitely structured light, and our innovation that we brought to the market is the parallel structured light. And Hanka will talk about this technology more in depth. But in general, we can say that the 3D scanning family provides the user with the possibility to scan static scenes in a high quality. We belong to the providers who have the best and most accurate point cloud, but where our innovation comes in is that we are also able to provide you with a crisp point cloud with no motion blur for also dynamic scenes. We are, the user that uses our devices can work with the point cloud or with the depth map, texture, or normals, but Hanka will speak more about that in a detail. What is the biggest advantage of our devices is that we are able to scan a different, big variety of objects and the different materials. As you can see on the GIF, our technology can cope with the scanning of plastics, cardboard, rubber, metal, aluminum, semi-transparent glass, and can provide you with a high quality point cloud. This slide we like to show to demonstrate to demonstrate the robustness of MotionCam 3D. If you want to compare the scanning performance of a time of flight, for example, it's very hard to do the segmentation, so localization of objects, because the edges are just non-present. If you want to apply scanner, a traditional structured light type of a scanner for moving object, the point cloud gets distorted. What is the added value of MotionCam 3D is that you are able to get a crisp point cloud suitable for further processment. When it comes to the USPs, so unique selling points in comparison with our competition, for example, there are four main that we like to mention. Definitely the first one is the fact that we are using red laser projection, which gives you big performance and the ability to suppress the ambient light. We are hosting the GPU NVIDIA on the inside of the body, so the processing time is rather short. We use carbon body, which allows you to keep the accuracy in different temperature conditions. And last but not least is that we are providing our devices in multiple different body variations. So, and that applies also for the PhoXi 3D scanner. And the PhoXi 3D scanner XL size is definitely the hit maker. This is one of the most used and sold devices of Photoneo, which basically allows you to scan from up to 4 meters distance. And that is very useful for if you want to pick objects from a deep bin and you need to manipulate on top of the bin with a robot. It's very, very hard to find something comparable on the market, and we are a true leader in robust scanning in this sense. Our devices are IP65. They have a PoE connection, and we are providing lots of APIs for plug and play, to further processing if you want to work with our point cloud. Both of them, MotionCam 3D and also PhoXi 3D scanner, they can work in one common ecosystem. So there is one driver for it. We call it PhoXi Control. That is free to download. You guys can download it and play with it. And it, like I said, it comes with multiple APIs and good documentation for your further processing. We have nice integrations with, for example, Halcon. We work with companies like Matrox, Adaptivision, PECAT, and many more. As I suggested at the very beginning, I will finish my part with the application areas, because I think this is the most important thing for you guys to understand. Not only how to use the technology, but also like where it can be applied and where it has been applied in the past. Unfortunately, we cannot mention all of our cool use cases, so therefore we also prepared some visualizations you will see in a minute. If we want to gather the application areas, we like to divide it into these vision-guided robotics and then into inspection and quality control. So let me provide you a couple of examples, and the first one is definitely, this is our bestseller. Majority of our devices are paired with the bin picking applications. The reason behind is that, as I already suggested, is that we have various field of use. Our devices can very efficiently scan even large areas and also small objects. They can be even small, shiny, as you can see on the picture. So, machine tending, bin picking are the applications that we have deployed hundreds of installations already. Obviously, depolitization is now a growing segment. E-commerce is growing, and our devices are really good for scanning the whole pallets. the accuracy and the density of the point cloud is really good for efficient segmenting of boxes. We also have great experience in applying our devices into the object handling. For example, this one is in IKEA in Slovakia, where we have been placing the furniture board to the boxes. Excuse me. I will just stop it. Sorry, there is a sound. We forgot to mute it. What we are showing in this video is the use case together that we deploy together with our partner BCN in Spain, where we are scanning tires. What I wanted to suggest by this use case is the ability to scan even black rubber objects and being able to manipulate those. On the next slide, there is also the video, so there might be a sound again. So excuse me for that. I will try to mute it as quickly as possible. Oh. Okay, and there might be two more. Sorry for that. So what we are demonstrating over here is that our devices. Mute it. Thank you. So the previous slide was showing the possibility to do the trajectory correction. So example that we used was the sniffing tool that was applied for heat exchangers. Our devices are really robust for scanning and giving the precise direction for the robot. The application that is shown over here at this video, maybe you can try to mute the sound. No, you can't, right? We have a control button over the video, but we will see that in the presentation that we will send you afterwards, is that our devices are being used also for navigating the robot for automated welding processes. We have there is a growing demand for doing this automation. If you have a good modular software capable of navigating the robot, our devices are good for detecting the trajectory for applying the welding. All right, let's see what is waiting us. It's muted over here. And another application that our scanners are being used for is the automated inspection. This is together with our partner PhoXi Vision, and thanks to the density of our point cloud, we can detect okay and we can tell if the device is, if the part is okay or not okay due to some dents or defects. When it comes to the use cases of the MotionCam 3D, one of the great examples of a great engineering that is behind the MotionCam is that you can do the picking and placing in motion. If you are able to synchronize the conveyor belt tracker together with the robot, you can be picking in motion and do the object handling also of the moving objects. Yes, good. Give us a second. Like this, for example. Another example of the application MotionCam 3D is the dimensioning and measurement of objects that are moving down the conveyor belt. There is a possibility to synchronize multiple devices in order to provide you with the dimensions of objects. Another great and emerging example that has not been, it was not possible to be solved efficiently with the existing devices is that using our MotionCam 3D, you can efficiently localize objects that are moving not only in a linear axis, but if there is an unexpected movement, let's say of these hangers on the overhead conveyors, you can efficiently localize objects hanging on those, or you can localize the hooks itself. Another great example where MotionCam 3D can be used is to scan large objects. Again, you can synchronize multiple devices, either let's say on top of the vehicle or from the bottom if you want to check for missing parts or the objects that should not be at the bottom of a vehicle, for example. Another great example is that with our devices, you can do the inspection of moving objects down the conveyor belt, even for areas where the conveyor belt cannot be stopped. The example can be, for example, press or stamping machine or the molding machine. With our devices, you can actually freeze the time, get the crisp point cloud of the whole object because we are providing with the area scan, and that can be done for further inspection. Another great example of how the device can be mounted or placed is that you can place our MotionCam or scanner onto the robotic arm. So we call it hand-eye approach. The advantage of MotionCam 3D is that you effectively don't have to stop the robot in order to do the segmentation or localization of objects. Because as you are moving around, you are constantly getting a point cloud without any motion blur. So this is the last slide that I'm presenting today. MotionCam 3D is a true innovation in the area of 3D scanning. We are able to provide you with a crisp point cloud for, let's say, real-time 3D modeling for the robot to understand his surroundings. Thank you very much for the attention. Now I'm handing the word to Hanka, who will guide you more in depth when it comes to the technology and application. There we go.
Thank you. So hello, my name is Hannah, and today I'm going to guide you through the practical training on how to use our 3D scanning devices and how to set up the parameters that can be used for efficient scanning. Of course, there will be several Q&A sessions and coffee breaks in the middle. So I will now speak for about 20 minutes or so. Then we will be having a short coffee break. Then I will finish this part of the training about the 3D scanning devices. We will be having a Q&A session after that and a coffee break after that. And then we will continue with the training for the PhoXi 3D meshing, which is our application for creating 3D models out of several scans, which will be also concluded by a short Q&A session. So we can move on with the practical topics. I hope that everyone can hear me well. And let's begin. So some of you already might have our devices at hand. Some of you might still be receiving them once they order. And here I would like to demonstrate how easy it is to set up the MotionCam 3D or your PhoXi 3D scanner, because everything that you need for setting it up is inside the box. So you will receive your 3D scanning device. There will be Ethernet cable, which will power the device via the PoE, the power over Ethernet. And you will also receive a PoE injector, which you can use in your installation or in your testing scenario. Let's take a look on the 3D scanning device. It has three main body parts. There is the processing unit. The processing unit contains GPU. It's NVIDIA Tegra GPU, which allows us to quickly and efficiently compute the point cloud directly on the device. So every processing is done on the device, and the resulting 3D data are sent over the Ethernet cable to your computer for your further use. Then we are having the projection unit. We are in the PhoXi 3D scanners. We are using the structured light technology. So the projection unit gives out the red laser light, and projects the patterns that are used to calculate the point cloud. The patterns are, of course, captured by the camera unit. On the MotionCam 3D, the technology is slightly different. We do not use the structured light but the parallel structured light. And this technology is based on our patented CMOS sensor that allows us to capture the 3D data of dynamic scenes and do point cloud reconstruction in a really short time of just 10 milliseconds. Once you receive the device, it's really just plug and play. So you connect the Ethernet cable with the power of Ethernet to one of the ports on the back of the device, and you will wait short time until it starts, and then you can easily take your first scan. Of course, it is necessary to use correct software package. I will get to that in a short while, but from this you can see it's just really easy to use the 3D scanning devices. As you could have seen on the previous slide, there were several LED lights on the center of the processing unit in the back panel, and these are used to signalize the status of the device. So usually when you power up the device, you always want to see everything green, because green means that everything is working correctly. But to better diagnose what is going on and understand the processes going on with understand the processes that are going on the device, there are several status LEDs which are important to understand. So on the first top LED, you always want to see green. But when you are turning up the device, it will be red for a short while until the device boots up. Then there is the second device, which tells us with green light that the firmware is ready. Again, once you are starting the device, the light is red for about a minute. It means that the firmware is still starting, and then it turns to green. If you connect to the device to your PhoXi control application, which is our main driver, then the light changes to orange. And then the last two LED lights, they are used to signalize what is the status of the connection, for the data connection. So for the correct operation, we require to use 1 gigabit Ethernet link, and you can see on the last LED light whether gigabit Ethernet is connected or not. This is really important, because if gigabit Ethernet is not used, then there might be breaks in the connection, or the processing time until the point cloud arrives to your computer might be really, really long. And the third LED light is the least important. It just shows you the activity on the link. So if the data is being sent, there is rapid flashing. If no data is being sent, then it's just flashing in a very short intervals. Let's move on. As I mentioned, we have one dedicated driver to all our scanning devices. This driver is called PhoXi Control, and you can download it for free at our website. We currently support Windows installations and also Linux installations using the Ubuntu 16, 18, and 20. Once you install the PhoXi Control on your computer, it is really easy to make your first scan. So we have already learned how to connect your device to the power and to your computer. You have already installed the PhoXi Control driver, and now we can make the first scan. So once you open the PhoXi Control application, we will see this given a short while. There will be the list of devices, and you can easily just hit the button to connect to it. The device will be connected, and then there are several main controls which can be used to trigger the scan. So of course, you can just go over to the main panel, hit the trigger scan button, and you will receive your first point cloud. From different, as you could have seen on the previous slide, there are several different main controls buttons, and I will explain how to use them in this slide. So as I have already mentioned, there is the trigger scan button, which allows us to trigger the single point cloud. So the device will project a series of buttons or make the acquisition if we are talking about the MotionCam 3D, and we will receive a single point cloud if we use this. The free run mode makes a loop of acquisitions. So the device will acquire the point clouds as fast as it can, or if we give it an FPS that we want it to acquire in, if we want to limit it, then it will acquire in that frequency. But yeah, if you want to scan continuously, which is usually used mostly with the MotionCam 3D, where you want to see the dynamicity of the scene, there is this button. And then there are two more important buttons. One is the logout button, which allows you to disconnect from the device, because the device only allows single connection from a single computer. So only one person can be using the device at a time. So if you want to free up the device to be used by your colleague, you have to log out from it. And then there is also the pause button, which can be used to prevent the device from taking a scan. And now let's take a little bit of look on what are the outputs and what to expect from them and how to set up the device. So the main output of our 3D scanning devices is the point cloud. The point cloud is a 3D representation of the scan surface, and it's just what it says. So there are several thousands and millions of 3D points in a space, which all have their X, Y, Z coordinates. So once you have your point cloud, you can take a look on what it looks like. You can easily zoom in to inspect the details on any part that you are interested in. Also, you can, in this right panel, you can change the visualization of the point cloud. So the natural visualization that we are giving by default is with the texture. So we are coloring the point cloud with the texture data, with the shades of gray that we captured during the scanning process. And you can, of course, change them to different. In here, we can see a shader that is based on the orientation of the normals, which I will be explaining later on. So you can go into the point cloud, try to zoom in to the different parts and change the visualizations to better understand how it looks like. The first and the foremost output that we are giving out is the depth map. In the depth map, we have the grayscale values of the pixel that represent the distance of the corresponding 3D point from the camera. This sentence might sound that it's really something complicated, but really it's not. It's just a 2D picture. And in the 2D picture, you can see in here, the white parts are the points which are further from the camera than the black parts or the very gray parts. This gives you a natural understanding on what the distance looks like in your scene. If you hover your mouse over a pixel, you can actually read the Z distance, the Z coordinate of each point in this current pixel value, which is on the right side in this panel. So if you hover over there, you can read the Z coordinate of the picture. The Z coordinate, of course, corresponds with the Z coordinate that you have in the point cloud. So the X and Y are not here. We are only having the pixel coordinates, so the pixel indices for rows and columns, not the X and Y in the millimeters, but we have the Z value in here. And then, of course, there is the texture, and we use the texture to put it onto the point cloud to better navigate you in orienting yourself on what you are actually looking at in the point cloud to really distinguish the 3D features. Our texture is in grayscale, and it has a direct relationship with the point cloud. So each pixel in our camera image has one 3D point calculated. This is the case in the PhoXi 3D scanners. Of course, in MotionCam 3Ds, the relationship is a little bit complicated because the technology allows us to compute around 2 3D points per 3 times 6 pixels. So we are having a little bit different mapping in the MotionCam 3D. So the texture is not so directly related to the point cloud, but the relationship is still there. The texture is usually used for feature recognition. And if you are having AI-based applications, then it can be used for segmentation and distinguishing different parts of objects that are being scanned. The grayscale value of each pixel can be, of course, again, read in this current pixel value field in this right panel over here. And last but not least, we are giving up the point clouds. With the point clouds is the normals. And to explain what is a normal is when you take a little part of the surface that you have scanned and you put a plane over this surface, and the plane is somehow oriented in the space. And the normal is perpendicular to these planes. So basically what this means is that the normal is giving you the orientation of the scanned surface with regards to the device. The normals can be visualized in the point cloud as ticks or as shaders. So in this picture, you are seeing the ticks. So you are seeing the normal vectors as they are. But in the previous picture, in the point cloud, I was showing you this green, orange to pink hued point cloud. And this shader is again based on the normals. So we can easily see which parts are oriented towards the device and which parts are oriented outwards from the device. The use of the normals is to gain the surface orientation, but they can also be used to estimate the noise and reduce it. This can be done by setting up I will explain the different behavior of normals in a situation where there is high noise in a later part. And there are several settings that can help you with getting rid of noise based on the normals. The depth map, the point cloud, and the texture, and of course the normals are something that we are giving up as a default. You can see here the screenshot from the PhoXi control, and there are 2 tabs. One tab is for settings and one tab is for structure. In the structure tab, you can select which outputs the device should be giving you. So by default, we always want to have the depth map on because the device is computing and transferring only depth map from itself to the computer. And the point cloud is actually calculated in PhoXi control. So you always should be having the depth map being sent, even if you set the depth map to not being sent, it will be sent because we have to calculate the point cloud for something, from something. So depth map, point cloud, and texture are there by default. On PhoXi 3D scanners, also the normal map is there by default. On MotionCam 3D, we want to have everything as fast as possible, and the calculation of normals takes some time. So on MotionCam 3D, the calculation is turned off by setting up this setting. So in this part of the menu, in the settings part of the menu, there is a setting that is called normals estimation radius. And for MotionCam 3D, by default, there is a 0 set for this parameter. To turn on the calculation of normals on the MotionCam 3D, you have to set non-zero value. Usually you would use 1 or 2 for the calculation. And then once you have this set up, you also in this structure have to set up the normal map to be sent, not just calculated, but also to be sent on the MotionCam 3D. Then we have 2 more optional outputs that can be given up by the device. One of them is confidence map, and I will be speaking about confidence map later on in this presentation, so everything about it will be explained. And then there is the event map, which is an optional output for the MotionCam 3D. And this event map will give you the information about at what time during the acquisition was the pixel captured. So this is the information that you can use for very time sensitive and synchronization tasks. This output, you will not find it on the PhoXi 3D scanners, you will find it only on the MotionCam 3Ds. Once you have your scans, you of course want to have as best scans as possible. And you have to evaluate them somehow. And this is a really important task in all our applications, because the application wants to have as best data in as short time as possible usually. So I will guide you through what to look for and how to look for it, and how to set up the parameters for the scanning in the best possible way to suit your application. So once you take a first look at your scan, you have to see if the scan is complete, if there are the details that are necessary for your application, and what is the noise. If the point cloud is really nice and you can distinguish all the features really easily, or if there is high noise and you cannot distinguish the features really easily. In here, I would also like to point out that all the scanning devices, since they have different body factors and different scanning volumes, which have to be respected. So if you are scanning any object, you have to place it inside the scanning volume of the device. So if you place the object too close, only part of it will be scanned. That is also true if you place the object too far away from the device. So please always take a look at what the position of the scanner is like with regards to your scanned object, and then try to position it correctly if it is necessary. Of course, there is also the resolution parameter in terms of how small feature can we distinguish on the object which is inside the scanning volume. The resolution depends on the scanning distance. So if we place the object closer to the scanning device, the resolution of the features is better than if we place it to the end of the scanning volume. This is of course also dependent on the scanner model. So if you want to distinguish really small feature, then you have to look for a device that has lower point size, value and lower body factor and smaller scanning volume. How to evaluate the scan? So there are several outputs that I was mentioning before, and they are there to help you evaluate the scan. So you have to inspect the various aspects of the data. You look at the normals, you look at the contrast, you look if there are all the edges of the scanned object that are necessary. And you, of course, have to check the light conditions. Because we are using the structured light and parallel structured light technologies, we are always emitting light on the object to gather the 3D data. If there are black objects or shiny objects, or if there is a lot of ambient light, this all has consequences on the scanning time and the scanning quality. And it is really important to learn how to evaluate all these aspects to get the best point cloud quality. To evaluate the data, there are, of course, different visualizations that you can use. So I was mentioning before the normal shader. Then there are the intensity multiplier, which allows you to see better if dark objects are scanned. And then there is the confidence map, which I will explain later, but it's used to evaluate the data computation quality. If we are looking on the completeness of the scan, it means that we are looking if the point cloud contains all important parts of my object. If the scan is incomplete, some data from the object is missing. There can be several reasons for the point cloud to be incomplete, and to be able to evaluate them, I will explain it throughout these presentations. So natural reason for incomplete scan is a shadow. We can see a shadow in this picture, and the shadow is caused by this cable because the light that was emitted by the projection unit only hit this cable and was not able to hit the parts that is behind it. So shadows are a natural consequence of the 3D scanning and are present in a lot, or I would say in all 3D scans. Then we have the underexposure or overexposure, which can cause incompleteness in the scan. And if we are talking about underexposure, it means that our light source, so our projection time, the amount of light that we have projected from the scanning device, was not strong enough to create a good contrast and to gather the 3D data. Or if we have the overexposure, it means that the light was too strong and the camera sensors was oversaturated by the light that was reflected from the scene. If we have a problem with completeness due to under or overexposures, there are several parameters that we can set up to change the light conditions and to help us scan the point cloud better. Then there are the details, and the detail is some small feature of the object. As I was saying before, the point size is the value that you should be looking up in the data sheet to see if feature of any size can be distinguished by the scanning device. So features that are bigger than the point size of given scanner should be distinguishable if the surface of the object is scanned properly. If you want to look if your scan contains details, you should think about visualization and visualizing the data by some color method. So for example, the normal shader. As you can see in this picture, there is just the texture shader used, and we cannot see this detail or this detail over here on the socket that was scanned. So really use all the options that are given to you to evaluate the completeness and details of the scan. Here we are getting to the noise, and we are seeing the confidence map for the first time. So I will shortly explain what is the confidence map. The confidence map gives you the information on whether the point has been scanned with good quality or not such a good quality, or with a good confidence. So in here we can see there are mostly black and white and shades of gray, but the white parts are the most important. So the white parts means that the inaccuracy of the points is larger than the threshold that we have given for the computation, and the black points, they are very accurately gained. So you can select the confidence map in the output structure, take a look at it, and see that the points here in the socket are slightly in the shadow for one of the parts, and they are not computed with such accuracy as the points that are over here, which are on top of the socket. If you hover your mouse over this confidence map, then again in the current pixel value, you will see the max inaccuracy setting. You will see the value of the max inaccuracy. There is a setting which is called max inaccuracy, which serves as a threshold for filtering out points. So for example, if you set the max inaccuracy to 2 millimeters, and the confidence map tells you that, for example, this point on this display here is 2.5, then the corresponding 3D point will be filtered out from the point cloud. This way you can establish that you want to use only highly accurate points in your data analysis, or that you don't mind a little bit of noise if you set it to higher value. And of course, then there is the normals and their behavior when the noise is in place. So let's, for example, look at this picture. In this picture, I have not shown the point cloud or the texture, but this part of the scan, there is a white cloth in here. And at this part of the scan, there was a black cloth. So the natural behavior of colors is that the black objects reflect lesser light. So it is harder to scan them, it is harder to get good contrast. And this is also reflected by the normals, because if we have lesser contrast, then also the orientation of normals is slightly more variable than if we have good contrast. So on the black parts, we cannot get as good contrast as on the white parts, and therefore also the orientation of the normals is changing a little bit more or slightly more than on the white parts. Of course, if there are completely noisy points in the point cloud, which can happen due to some reflections, it is very likely that these points will have the orientation of the normals to completely nonsensical way, and they can be filtered out then. Important aspect of 3D scanning is position of the device. Especially if we are talking about using the 3D scanning device with shiny objects. As you can see here, the light that is emitted from the projection unit is reflected directly to the camera. We can distinguish which parts are directly reflecting to the camera by seeing this white lens flash. This means that usually there is some overexposure in the scan. but sometimes it is really hard to get rid of it. So if you are positioning your device in a good way, it really comes down to distinguishing which parts are being illuminated by the structured light, by the pattern. So if we are able to distinguish the white part with the black part, then we get a complete point cloud. But as we can see in this picture, the light bleeds through the black stripes. And that means that in those parts where there is the bleeding of the light, the 3D point cloud cannot be reconstructed because the pattern of the stripes that are emitted by the scanner is broken. This also happens with the MotionCam 3D, of course, with the parallel structured light technology, because we are still using laser line to scan the whole area to gather the 3D data. So by changing the scene or the position of the scanner, you can get a really different results from your scanning. So you can either get a complete point cloud, or you can get a slightly or even more noisy and more holy point cloud. Okay, let's move to some different topics. And when you are scanning, you of course want to change the parameters to get as best quality of the scan as possible. But usually when you are changing the parameters, you usually are increasing the scanning time. And that means that, for example, if you are in a robotic application, then the cycle time is affected by this. So always, when setting up the scanning parameters, try to understand what you are doing, how is it affecting the scanning time, and always try to find a good way between the scanning time and the quality of the scan. Because sometimes the scan can be improved further, but it would mean that the scanning time would be much higher. But in some application, even lower quality of the scan can be used to do the use case that you are supposed to do. So the scan when you are scanning, the total scanning time is the sum of acquisition, which is defined by the capturing settings. Then there is the computation. So all the 3D data that have been, or the data that have been gathered by the device are computed on the integrated GPU. And then there is the transfer time. So the data are transferred from the device to the PhoXi control. Here I would like to really distinguish that on MotionCam 3D, the acquisition time for one scan can be just 10 milliseconds. Of course, you can set up a higher exposure time and do a higher exposure. But we are going as fast as 10 milliseconds on acquisition in MotionCam 3D. And we have the total output of 20 FPS with this device. On PhoXi 3D scanner, in the best case scenario, one scan is 250 milliseconds. So there is a really large difference, and the PhoXi 3D scanner can output data at total rate of 3 FPS. You can learn how long each part of the scan took in this frame information, which is usually located in the right panel at the bottom. So you here see the time it took to acquire the image, the time it took to compute, the time it took to transfer. And then there is something that we call the GUI latency. It's how long it took the computer to visualize the data.
But this can be turned off, right?
Yeah, it can be turned off, yeah. Let me explain something about the scanning parameters. So I was already talking about the structure part of this menu, and now let's tell you something about the settings. So the MotionCam 3D and PhoXi 3D scanner have a slightly different set of scanning settings. So on MotionCam 3D, we have something that we call the general settings, where we select which type of acquisition we want to do, because the MotionCam 3D can work in the highly dynamic mode, which we call the camera mode, which is able to output the 20 FPS. And we can also turn the device to so-called scanner mode, in which the device works the same way the PhoXi 3D scanner works. So it uses the projection of structured light patterns to acquire the 3D data. And its FPS is changed to the same level as for the PhoXi 3D scanner. So we have a menu that allows you to change the operation mode and some general settings such as laser power or maximum FPS. And then we have the dedicated mode menus where you can set up the acquisition settings for each of these modes, which is reflected here in the PhoXi 3D scanner as the capturing settings as in these basic and advanced settings. And then we also have some processing settings and coordinate settings, which are the same for both of these devices. So let's take a look on a little bit closer. So as I was telling you, in this general menu on the MotionCam 3D, you can switch between the camera mode and the scanner mode. And of course, you can also just get the 2D texture from the device if there is the need. But usually these two modes, the camera mode and the scanner mode, are used. And then there is, as I was saying, there is the separate acquisition settings for the camera mode and the scanner mode. And the scanner mode acquisition settings are mostly the same as we would see on the PhoXi 3D scanner. So let's go a little bit deeper. And let's see what are the settings in the camera mode. So in the camera mode, the main setting is the exposure. And it allows you to increase the amount of light that is emitted from the scanning device. And of course, it also changes the time that one scan takes. So in here, we can see that the exposure is set to 20. As I was saying before, we can go as low as 10 milliseconds. And up to 40 milliseconds is allowable by the MotionCam. So you usually want to set up longer exposure times when we are scanning objects that are darker or further away, but always have in mind that setting up higher exposure time will result in a slightly lower FPS from the device, so that the throughput of the data will be slightly lower. Then we have the scanner mode settings, and these are mostly the same as the PhoXi 3D scanning parameters. So we have the shutter multiplier, which also changes how long the scan is required for. So it allows us to multiply the time that is used for scanning, and also multiplies the amount of light that is put out from the device. So the more light, the easier is to get good contrast on black or dark objects, and the better is the output quality of the data from such objects. Then there is the scan multiplier, and the scan multiplier repeats the scanning sequence and averages the results that we have gotten from these two sequences. And it allows us to have better dynamic resolution. And it also allows us to get rid of a little bit of noise. Then there is the coding quality parameter, and this affects how many patterns are we using to capture the 3D data. So this can really affect also the scanning time, because if you are going for quality, then you are using more structured light patterns. And this means that the scanning time is higher. If speed is necessary, then you can change this setting for a lower value, where less structured light patterns will be used, and the scanning will be done faster, but of course the quality will be a little bit lower. Then there is the coding strategy. I will show you what this coding strategy just does in a further slide. And then there is the texture source. The texture source selects the light source for the texture. I was already mentioning that the 3D scanning is done by a laser light. Of course, the laser light has some disadvantages when it's captured by the camera. And usually the disadvantages is that there are speckles, which are some sort of artifacts in the pictures. And the texture does not look so good when it's taken by the laser. So inside the projection unit, there are LED light emitters. And these light emitters are used only to capture the texture. You can see when you look on how the PhoXi 3D scanner is scanning, you can clearly distinguish that the device goes through a series of patterns, and then there is the brief flash, and this is the LED light that takes the texture. I will show you the differences between these two texture sources, these two illuminations, in a further slide. I was already explaining about exposure, which is the parameter that prolongs the scanning time and gives you more light into the scene. In the scanner mode or on PhoXi 3D scanner, the same parameter is called the single pattern exposure, because since we are projecting a series of patterns, we are increasing the time and the amount of light for each of these patterns. So therefore, it's called single pattern exposure. And last but not least, there is the resolution, which is the maximal number of 3D points that we can have in the output. So in here, we have a comparison between different exposure time. So we are scanning a darker object, and you can see that the parts of the object that are a little bit further away from the device in this scan with lower exposure time do not have that many points as in this scan. So really, the only thing that needed to happen to get a better scan of such an object was to increase the scanning time or the exposure time or the single pattern exposure time to get a result like this. The resolution, there is a difference between the resolution on MotionCam 3D and the PhoXi 3D scanner. On the MotionCam 3D, you cannot change the resolution as it is as the single parameter, but it's tied to the operation mode. So the resolution is different in the dynamic mode and in the static mode, or in the camera mode and the scanner mode. So in the scanner mode, there is higher resolution of 2 megapixels, and in the dynamic mode, in the camera mode, there is 0.9 megapixels resolution. And this is something that is related to the way that we are acquiring the data in these different devices. So on the motion cam 3D, there is not the behavior that each pixel has its own dedicated 3D point, but the ratio is a little bit different. And in the scanner mode, we are of course using all the pixels in the 1:1 ratio. So each pixel has its own 3D point. So the resolution is tied to the operation mode and also to the output topology and to the sampling topology, which can be changed for the motion cam 3D. On the PhoXi 3D scanner, we can set whether we want to use half resolution or full resolution. So the full resolution is 3.2 megapixels and the half resolution is 0.8 megapixels. The advantages of the half resolution is that the computation is done very fast because there are so many less 3D points. So it takes a lot less time to compute the 3D points, and it also takes a lot less time to transfer it to the PhoXi control. And the difference is apparent. On full resolution, we have a lot more. The sampling is a lot higher than in the half resolution. So with half resolution, we are doing something that is called binning, and the pixels are being binned, and the information gathered by this binned area is actually computed. So it's giving us a little bit also higher or less noise if we are using the half resolution. And here are some examples of the scanning settings that I was also talking about before. So we have the shutter multiplier in this first part. And the shutter multiplier, as I was telling you, gives more light to the scene or multiplies the scanning time, multiplies the amount of light, which is apparent in this picture, especially in these white or very light parts of the picture. You can see that with higher shutter multiplier, the scene is much lighter in these areas. Then there is the difference between the textures. So we have the LED texture and the laser texture. And in here, you can see that there is the noise I was telling you about, the speckles in this texture, which are caused by the properties of the laser light. So the LED light does not have such a property that it would create these speckles. Therefore, it is much nicer. So if you are having an application where texture is important, where you want to segment out the data or distinguish the edges or something like that, you should be using the LED texture instead of the laser texture. And then we have the coding strategy, which can be changed between a normal setting and interreflection setting. And this setting changes the frequency of the light stripes in the patterns. So the normal coding strategy has the patterns from low frequency to high frequency. So we have bands that are really thick, or we are starting from bands that are really thick until we have really small ones, really thin ones. And in the interreflections coding strategy, we have the frequency is very similar throughout all the patterns. And this is important because when we are projecting such a thick bands of light, when the frequency is lower, we can be struggling with illuminating by reflections. So when the light hits the scene, it reflects back. but it might not reflect back only to the camera. It might also reflect to a part of the scene. So it causes a secondary illumination. And this interreflections coding strategy sort of gives you an advantages in situations like this, because there is not such high probability of interference between the project, between the secondary and the primary illumination. If you want to check for the light conditions in your scan, there is also the texture source called focus. And these settings will put one of the structured light patterns as your texture, and you can evaluate how is the contrast in your scanned object. So in a good scan, we have a good contrast between light stripe and dark stripe. This is explained in these pictures. So if we look at this part of the picture in the red rectangle and look at the current pixel value, we see that the amount of light is really high. And if we look on the picture in the bottom and look on the dark stripe, there is still some amount of light in here. And of course, this is the light part of the object. So we are scanning something white or something very light. And you can see that the contrast between these two is really easily distinguishable even by your eye. If we move to the dark part of the object, by the naked eye, it is really hard to distinguish whether there are or there are not any light stripes. If we would zoom in, it would be much easier. But there is, of course, the different, you can see on the illuminated stripe that in here, I'm showing you the illuminated stripe, even if you cannot see it right now. The value is still different from the unilluminated. So we are still able to get some contrast. Therefore, we will be able to get the computation of the 3D done even on this part. If you cannot distinguish the patterns or the light part from the black part on your scan, it means that there is no way for the computer algorithm to do it either. And the computation will fail. So we will not get any 3D data. Let's talk a little bit about what to do and how to distinguish whether you once you establish that you do not have good light conditions, what you can do with those. So if you scan really light objects, you can be easily dealing with overexposure. So the camera sensor is receiving more light, more photons than it is able to process. You can see the result of such overexposure in this picture. So in here, a lot of light is being reflected directly to the camera, and the light is bleeding through the patterns, through the dark parts of the object. And in the point cloud, it results in this type of hole. So we have incomplete point cloud, and the incompleteness can be seen from the texture source focus as a really this high white block of pixels. If we lower the scanning time in these conditions, or if we set up lower laser power, then we are able to distinguish there is not the bleeding of the light between the illuminated and unilluminated stripes, and we are easily able to distinguish the patterns, and therefore the reconstruction of the 3D data was successful. You should always be avoiding overexposure, and if you hover over the texture, and see the current pixel value, and the value is close to 4094. It means that the camera sensors and the camera pixel is oversaturated. So this is the maximum value, and that you should be looking into lowering either the shutter multiplier or the single pattern exposure or the laser power. So the laser by default is set to its highest possible value, and you cannot increase it, but you can decrease it if it is necessary for your application, if you are dealing with overexposure. Then we can have the underexposure. And the underexposure means that the light reflected to camera does not create sufficient contrast between light and dark stripes. We can see it in these parts of the scan, that the light and dark are sort of bleeding into each other, they are disappearing. And also the reconstruction in these parts of point cloud was not successful. So if you are dealing with the underexposure, it means that the light is not sufficiently reflected back to the camera, and you might want to set higher shutter multiplier or single pattern exposure, prolong the scan, multiply the amount of photons sent out by the device, and as a result, have a better 3D point cloud. Interreflections is something that I have a little bit touched upon while I was talking about the different coding strategies. So as I was telling you, the whole principle of 3D scanning is that the light emitted by the projection unit is captured by the camera, and it's captured because it's diffusely reflected from the surface. So we can see in this picture that the light, which is hitting this part of the bin, because we are having a bin in here. So this part of light is reflecting like this over this component. And in here, we should be having the dark stripe. But the light, the contrast and the amount of light, the saturation is the same in this part. And this creates so-called interreflection artifacts, which we can see over here. And it means that the 3D reconstruction is not good, does not reflect the surface as it should be reflecting. There is no trueness to this point cloud. Of course, this interreflection usually happen in places where the geometry of the object changes suddenly. So naturally, they would be occurring inside of bins or where there are sharp angles, and they are caused by the secondary illumination. And of course, you can use the interreflections coding strategy to slightly mitigate them, but they would be still happening. But we have a function or filter that is called the interreflection filter, which filters out these sort of disjointed parts of the point cloud. You can set up its strengths to suit the situation that you are dealing with. So this was everything about the important scanning parameters and how to understand them and how to use them for your advantage. And now something about saving the data. There are several different file formats that we are supporting with our 3D scanning devices. We have two native formats. One is the Photoneo RAW data format, which is output by both PhoXi 3D scanners and MotionCam 3D. And then there is MotionCam 3D RAW data format, which is only, as the name suggests, output by the MotionCam 3D. And then we are, of course, supporting different recognized file formats. There is the option to save the PLY, PTX, TXT, and TIFF files. And there are different ways to save these scans. So you can either save the scan as they come. So you trigger scans and you decide, oh, this one I want to save. So you hit the save button and you manually pick up which file format you want to save as. Or you can record all the scans that are coming from the device. This is done via the function of automatic saving. So there is a pop-up which allows you to set up what type of data you want to save, in which folder, in which naming convention, and then you hit the record button, and all the frames that get to PhoXi control from that time you have hit the recording button will be saved to your hard drive. Then there is the diagnostic scans. There is an option if you are having trouble with getting a good quality of scans and you want us to evaluate them, or if there is some kind of problem, there is the possibility to save automatically diagnostic scans. These diagnostic scans do not have to save all the scans that are coming to the device. You can set up how many scans are being saved or how often they are being saved. And you can also save different types of diagnostic outputs, which can be analyzed by our team to help you figure out the problem. So this is mostly for problematic situation or when you want to understand the behavior better. So I was already talking about the recording, but there is one aspect that I wanted to mention, which is important, of course, mostly for the MotionCam 3D, because we are having the high rate of data coming in. And if you want to save all the data that is coming in this high rate at the 20 FPS, you should be using this MP-RAW or the MotionCam 3D native format, which allows you to save multiple frames in one file. This is, of course, can be recorded back at any time. So once you save it to your disk, you can load it into PhoXi control and view the data. And this is best because it is good for capturing the dynamic scene. So if you are capturing something that is moving, you should be using the MP-RAW. Then there is the P-RAW files, and these are good if you want to save the individual scans and individual frames. The P-RAW is not able to handle the dynamic scenes. You will not, it is able to save each scan, but you will not able to see the movement. It will be just a static scan once it is saved. For if you are recording into P-RAWs with MotionCam 3D during a dynamic scene, the disk writing speed is limiting. This is of course true if you are also saving different file formats or several file formats at a time. The disk writing speed is always limiting, so some files might be omitted if you are saving too much data in a very short period of time. So yes, if you want to save as much data as possible at a higher rate, you really need a powerful computer with a powerful disk. Hello everyone and welcome back to our training. Today we have one last topic to discuss, which is the PhoXi 3D meshing. I hope that you are sufficiently refreshed and able to listen to the topic for a short while. And then we will, after finishing what we have to discuss, there will be another short QA. We will also answer the questions that are already there from the previous QA sessions. So don't worry if we are not answering them right now. Okay, so let's go and talk about the PhoXi 3D meshing. So the PhoXi 3D meshing is a C++ library that we are offering to work together with our PhoXi 3D scanners and MotionCam 3Ds. And this library is intended for surface reconstruction out of multiple scans. So using this software, you are able to merge multiple scans together and create in this way a 3D model out of an object that you have scanned. The 3D models can be then further used in different use cases, such as inspection or reverse engineering or 3D modeling. And I will try to talk a little bit about them. This C++ library also has a graphic user interface, which we are giving to use to you for the evaluation of the product and its functionalities. And the 3D models can be exported to standard formats like STR or PLY, which are recognized by large scales of 3D applications. So let's quickly take a look on what 3D meshing is and how it works. So we just load different scans from different taken from different perspectives, and we can see that they are pre-aligned. They are taking different parts of the object into account, and we will quickly create a model out of them with a simple reconstruction of the surface. So there are several steps to this function to how to create the model, and I will be explaining them throughout this presentation. This video is a little bit sped up to give you just a teaser of how easy it is and what the expected result is. So let's move on. I was telling you that the 3D models can be used in different use cases, and I want to shortly talk about why and how. So if you take a single scan, as you can see in this first picture, there is only the data from the surface that is turned towards the scanner. If we are having a task to see whether my piece has been machined correctly or if it has correct shape, so I have a CAD model of a part and I want to compare whether the part that I have produced is the same as the model that I have, the gold standard. I cannot do this by just having a single scan from the piece. I have to have multiple scans and the 3D model. So in the inspection use case, I use the 3D model to compare whether I have correctly produced the piece that I was machining. Then we have the reverse engineering object. And here the task is to create high precision 3D models. So for example, if we have an automation project that has been running for some years and I want to sort of move it into a digital era and I want to automate it in a computerized way, I may require a 3D model of a complicated object. So in this use case, it is really easy for me to just take the part that I am creating on my line and to scan it, create a quick 3D model. And this 3D model can serve then for the CAD engineer to create a new 3D model with correct measurements for the upgrading of the line in the factory or cases like that. And then we have the 3D modeling use cases in which there are, for example, historical heritage sites that needs to be preserved as a 3D data, or for museums which are having some artifacts and they want to have the 3D data, save the 3D data, save their shape. Then we can have need for 3D models in retail, which are then used for marketing purposes. Some e-shops want to have 3D models on their site to show the different parts and to allow the user to see what the object is like. So the PhoXi 3D meshing is also intended for these verticals. I will now talk a little bit about the hardware setups and what devices and situations the PhoXi 3D meshing can be used in. There is the setup in which we do not have any automatic way of moving the object or moving the scanner around the object. So we are using the marker pattern to calibrate the system. This will be mostly used by you if you are evaluating the library and evaluating its functionalities. Then you don't need the robot, or you don't need the automatic rotary table, which are displayed on this or can be used together with the software. You just need the marker pattern, which is standard part of our portfolio and is available through PhoXi Control. And this marker pattern can be used for the creation of the 3D model. Then we support the use cases in which the object is rotated on an automatic rotary table, and use cases when the scanner is placed on a robotic arm and the robotic arm is moving the scanner to a different positions in which the scan is being taken to see all the different parts of the object that is being scanned. The PhoXi 3D meshing can be used with all 3D scanning devices in Photoneo portfolio. So of course there is the PhoXi 3D scanner and the MotionCam 3D, and you can also combine these two, or you can combine different models or even different sizes, different models, use single device or multiple devices, and all of this is supported by the library. Let's move on to the software configuration and setup. So the first part that needs to be taken care of when you want to create a model out of your object is to somehow calibrate the system. So the first way, or the easiest way that does not require such a lot of material or a lot of resources, is using the marker pattern. In this, the prerequisite, the requirement is to have the marker pattern visible and recognized in each scan. So as we can see in this picture, there are two devices which are looking at the object from different positions. There is the marker pattern visible for both of these devices. And by recognizing the marker pattern in the scan, we are able to overlap the two scans correctly. This approach supports multiple devices, as you can already see in the picture. You can create a full model. So I will talk about it later on, but also the parts of the object that are in contact with the table can be scanned. And it's supported via the graphic user interface and also the API. The limitation of this approach is that if the object has to be smaller than the marker pattern, or you have to be really clever in using the marker pattern if the object is larger. Then there is the second approach with using the rotary table. And in this setup, to calibrate this setup, the marker plate is rotated on the table. So we take a scan of the marker pattern in this position, then we rotate it slightly, and we take another scan. These two scans, and also there can be several more of these scans, and also the recognized circles on the marker pattern are then used to calibrate the system. And the resulting calibration is that the origin or the coordinate system of this setup is moved to the center of the rotary platform, with the Z direction being up from the platform. This setup supports multiple devices, so we can also calibrate second scanner in this way, together or with the primary one. We are able to get the full model. The API and the graphic user interface both support this use case. And you can use any custom rotary table that you have on your hands. This is something that requires some programming skill and programming attention, because we have two incorporated rotary tables, two brands. But if you want to use your own kind, you just have to prepare an executable that you will copy into a specific direction, and the program will be able to work together with your rotary table.
Hanka, can I ask you a question? In this case, the marker pattern needs to be used only for the calibration, and then when
then it can be removed from the scene.
Okay, cool, thanks.
Then we have the use case with the robotic arm, where the scanner is placed on the robot arm. And the first thing to calibrate such a system that you need to do is the hand-eye calibration. During the hand-eye calibration, as you can see, the marker pattern is scanned from several different positions of the robotic arm. And by recognizing the circles from these different positions and knowing the joint positions of the robotic arm, we are able to transform the point cloud into the 2-point space. So it's after the 6th link. So to perform this sort of calibration, you have to scan the marker pattern from different poses. And for the meshing, so once you have this hand-eye calibration done and you want to do the meshing, you have to supply joint position for each scan. So if you are moving the robot over the object, you have to know the joint positions, and based on these joint positions, you have to transform each scan that you are taking with the device. This use case is supported with creating the full model, and you can use it via the API, not the graphic user interface. If you want to understand how and why these calibrations are necessary, I will explain it in these two slides. So once we take scans from different positions of the scanning device, or I turn the object inside the FOV of the scanner, I have no correspondence between these scans. If I want to cover the object as a whole, I of course need multiple scans. And why I do not have any correspondence is because the point cloud is based, or is in coordinates based on position of the camera. So if I put these two scans together, they are overlapping in their origin, which is inside the camera. And to find the relationship or the correspondence between these two scans, I have to somehow know how to transform the scan, to apply correct transformation. So I have to know either have to know precisely how I have moved the object and apply correct translation and rotation, or I can do it by knowing the position of the robot joints or the position of the mark pattern. And as a result, I have a calibration that is automatically or can be automatically put over the scans. And this way, we already get pre-aligned scans, and there is the relationship and correspondence between the features of the object on the point cloud, and we can easily create the model. If you want to get more familiar about the coordinate spaces and about the marker pattern, then please take a look on Appendix 1 in PhoXi Control User Manual. The topic is there explained there in depth, so you can take a look to understand it better. Now let's take a look on what to and how, after we have calibrated, on how to create the model. So as I was mentioning before, we can work as a one-click solution. So once we have acquired the scans and loaded the scans, this can of course be scanned directly from the application. They do not have to be loaded as a files. So once we have all these scans, so either by doing the scanning or loading them, it only takes one click of a button and a really short period of time to reconstruct the full model. In some use cases, we were able to get to 10 seconds of scanning time and 10 seconds of processing time to get the full model of an object. So as you can see, we now here have the reconstructed model. Then there is the second use case, which is of creating the full model. So in here we can see we are scanning live the object. This is also of course sped up. Then we turn the object on the table and scan it again. And these two are automatically located. These two series of scans are automatically located and oriented to fit together. And now we can see that there is the option to go through the whole pipeline. So the pipeline has several steps, as I will show you later. And we can choose how many times or in which way we want to run the reconstruction. As for creating the full 3D model, here I feel it is necessary to say that the recognition of the two sequences of the scan requires the model to have some features that will enable correct putting together of these two scanning sequences. So if you have an object that does not have much features or has large planes and things like that, it is really hard for this algorithm to work correctly. So as you have seen in the video, the whole pipeline consists of several steps. We have already calibrated the system, so calibration has been done. And now we want to do the scanning, and we have to do the alignment, we have to do the filtering, and then the surface reconstruction and trimming. So the scanning can be done either to create a simple model. In the simple model use case, you do not have to scan, you do not scan the complete model, and you do not have to scan it from all the sides. So you just scan all the parts that you think are necessary to be in the model, and you can use one or multiple devices. If you are scanning for full model, then you have to do several sequences of the scanning. So you scan from all necessary angles from one or multiple devices, you turn the object and start a new sequence of scanning. You can add as many sequences of scan as you feel is necessary, But this, of course, will prolong the time it requires to compute the surface of this model and process everything. The second part of the scanning or the pipeline is the alignment. So the calibration that we have done is giving us only a rough alignment. And during the alignment, as you can see in this picture, the scans, the several different scans that are already a little bit overlapping or overlapping roughly are moved to be as close together as possible. This is done by using the ICP algorithm, which is the iterative closest point. And the algorithm that we are using is pretty robust and is able to move the scans correctly, even if the overlap is not really nice. Then there is the filtering part of the pipeline, which removes the background that we have scanned and also removes the camera position artifacts. So once we are scanning, especially if we are scanning objects that have a lot of angles and a lot of features, there can be different interreflections and reflections and things that create artifacts in our scans. And we want to get rid of them during the filtering. You can choose whether you will run filtering before alignment or after alignment. In the automatic pipeline, the alignment runs first and the filtering runs after it, but you can do it with filtering first. As for the filtering, there is the important information that all the points that are not in the neighboring scan will be filtered out. So each part of the object has to be present in at least 2 scans for the point cloud not to be filtered out during this phase of the pipeline. And then we have the last step, which is the reconstruction and trimming. So during the reconstruction, triangles are overlaid over the points in the point cloud. The reconstruction can be done in different qualities. This here, of course, also depends on how fast you want to have the result. So if you are going for fast reconstructions, then there will not be such details, but it will be really, really quick. If you are going for quality, then you of course have to count with a longer time for the processing to go through. Usually we are using triangles to represent the surfaces, and the triangles are connecting the dots to best represent the surface that is there. Of course, sometimes it happens that the triangles overlap a surface or connect together points that do not represent the surface correctly, and then these triangles are usually cut out during the trimming. PhoXi 3D meshing is able to export different file formats that are widely used, such as PLI and STL. So the output can be then further used in any program that is used for processing of 3D surface data. If you want to get started with the PhoXi 3D meshing, you can contact our Photoneo sales representative at sales@photoneo.com. We have trial licensing available, so you can try this on your own and see if it suits your needs. Thank you for your attention and for attending this webinar.